So let's take a look at public key infrastructure and the technology that lies underneath it. So a lot of the mathematics depends on modulus arithmetic. And if you remember, the way it works with modulus arithmetic is that suppose I've got a length of string and the length of string is, say, 40, then we wrap the string around, and so it'll go around 3 times, and then it'll actually reach to the number 4. So we say that 40 modulus 12 is equal to 4. So basically we can add any multiple of 12 to our number. So for example, if it was 40 and then I made it 52, then we'd go around 4 times now. 4 12 is 48, and 52 would get us to 4 again. So 40 and 52 have are congruent, if you like, modulus 12. Okay, let's see how this is used. So we need some background on modulus arithmetic. So we've seen that if b for some modulus p, if b is not congruent with 0, then we can solve that ax equals b with respect to that modulus. And we say that a mod p is invertible. So this a over here, I should have put that in quotes, but a mod p is invertible. Let's take the case where it's 1. So here we've got 1 mod p, so I chose b equal to 1. And now I think you can see that a times, typically it would be a to the minus 1 or 1 over a here. But because we're doing modulus arithmetic, x can actually be a non-zero value. But there is one that will give us a 1 mod p. So we'll see that. Another way of writing this is we can add any multiple of p because we're taking moduluses of p. You saw that with the clock, that any number at times, in our case 12, there with the clock, so p would be 12. Y could be 1, 2, 3, 4. It won't change the value of ax with respect to modulus p. Okay, so an equivalent statement is that a times x plus y times p is 1 in mod p. Another way of saying this is that a and p are relatively prime. So they have no common denominator. As I said, a times x, 1 mod p, is equivalent to there being an inverse. So if x has an inverse, then this is true. Okay. So let's take a look at Fermat's little theorem for a prime value, p being prime. So if p is a prime value, then a can take all the values up to p minus 1 because none of them divide into p. Yep. So they're relatively prime with respect to p. So let's take q now as being a times s. So s 1, 2, 3, 4. Q will be a, 2a, 3a, 4a up to p minus 1a. Let's suppose now that k times a equals 0, where k lies between this. Well, we know that a isn't divisible by p, right? Because it's prime relative to p. And k takes the values 1, 2, 3, 4 here. K lies between 0 and p minus 1, so k also is not divisible by p. So neither k nor a are divisible by p, so ka isn't divisible by p. Okay? So there is no non-zero element here in q. but we need to show that each of these values is distinct with respect to modulus p. So let's suppose we have r times a and s times a. Basically, we need to show that this cannot be true. R minus s times a can't be 0 mod p. The only time it could be 0 if r and s are equal, but we've said that they're not equal. Now, r and s also is not a multiple of p, and a is not a multiple of p. So this can't be true. So r and s must be distinct. So this means that each of these is distinct with respect to modulus p. Yep, r minus s is not divisible by p, nor is r minus s 0. So every element in Q is distinct. And so that means that these must just be in a rearrangement with respect to mod p, remember. So these numbers may be greater than p, and when we divide, these numbers in Q are exactly the same numbers as we saw in S, but they're rearranged. Okay. Now that means that if we multiply all those numbers in S together, we get p minus 1 factorial. So we get 1 times 2 times 3 up to p minus 1. If we take them in Q, we can take p minus 1 A's. So you have A, 1a times 2a, and so we can take those out and we get a to the p minus 1, and we still get the p minus 1 factorial. And this is all with respect to mod p. Now we can divide through by p minus 1 factorial because it's not 0 and it's not divisible by p. So we get a to the p minus 1 is 1 mod p. Or a more useful result maybe is that a to some power p gets you back to a with respect to modulus p. That's really nice. And if we have a message a and we raise it to some power, we might be able to get the message back. So you can see that this might have some implications in encryption. So that was called Fermat's little theorem, and he proved it in 16 something. So now Euler comes along and he wants to extend this to non-prime values of p. So remember, at the moment we've got a to the p equals a mod p, but p here is assumed to be prime. We've only shown it so far for prime numbers. Now can we show it where p is not a prime number? Let's see. So the key part that we need to remember in Fermat's proof was that we need a and p to be relatively prime. So a is this number that we're going to raise to a power, and p is the modulus. We're going to take modulus p. So these must be relatively prime. Then there can't be a common factor to them. If there's a common factor, we can't have this a times x equals 1 mod prime. But if there's no common factor, then this can be true. Even when, here I've put an m instead of a p, but even when this is not prime, they're likely to, we can solve this. Okay, so just remember that. Now, Euler developed a function. He said, let's suppose we have the numbers n, then let's count how many numbers are relatively prime with respect to n. So if n was a prime number, there'd be n minus 1. So he called this function the Totient function. So the Totient function for a prime number, n, is just n minus 1. But in the case of other numbers, for example, if we took n to be 12, obviously 2 divides into 12, 3 divides into 12, 4 divides into 12, 5 doesn't, 6 does, 7 doesn't, 8 has a common factor, 9 has a common factor, 10 has a common factor, and 11. So the Touchin function for phi 12 is just 4. We have 1, 5, 7, and 11. Now we can play the same game with these numbers that are relatively prime to n. So let's call them S again. So we have U1, U2, U up to little n, but that may be much smaller than big N. Okay, as we saw in the case of n equals 12, there were only 4. We had 1, 5, 7, and 11 here. So there are only 4 of them. But now let's play the same game and multiply these by some value A. Now A must be relatively prime to big N. Okay, so they shouldn't share a factor. Okay, so we know that all these little items UI with respect to mod n, in this case say 12, we can't have them being 0. They don't share any common factor. So every one of these AUIs is definitely non-zero, and we can show that every element in Q is distinct. So it must be just a permutation of the elements in S. So Q and S contain the same elements. Okay, so this means we can again multiply these units together on both sides. Now again, these won't come to factorial anything. These will just be multiplied together, and these are bound to be the same ones again on the right hand side. So what we have is we have the number of A's in Q is just the Touchin function phi n. So if n was 12, this would just be 4, a to the power 4, and a to the power 4 equals 1 mod n, 1 mod 12. Let's take a look at this. And of course we can just multiply through by a, and we get this other version. But let's consider now modulus 12. Let's take that. As we found out, the Touchin function for that is 4. So a to the 4 should be 1 mod 12. And we need to look now at what the units U1, U2, etc. can be. They can be 1, 5, 7, or 11. So first let's check these out. So 5 to the power 4, 1 to the power 4 is obviously 1 mod 12. But 5 to the power 4 is 625. It divides by 12 52 times, and we get 1 over. So that's correct. 5 to the power 4 is 1 mod 12. 7 to the power 4, again, is 12 to the 20, 12 times 20, plus 1. So it's correct. And 11 comes to 14,641, and that's 12 times 1,220, plus 1. So that works. Now, let's see what happens when we multiply through by some A. So Q, so we have S, 1, 5, 7, 11. Let's multiply every element of S by 5. So we get 5, 25, 35, 55. Well, if we look through here, we see 5. Now 25 is a multiple. If we take the modulus 12, 2 12s are 24, it's 1. 35, 2 12s, 24, and 11 go to 35, so that's 11. And then 55, we have 48, 4 12s, 48, and that'd be 7. So this is just S, but in a different permutation. Now we've got 5, 1, 11, 7. The same when we multiply S by 7. And we can't multiply by any other numbers, because when we take our A times whatever unit, A, it must be relatively prime to 12. So we can only have 5, 7, and 11. And if you go through this, you'll see that these are all just come to the same values as in S, but in different permutation. So we've shown that this is indeed true, that this can be extended to non-primes, and we can even extend it further now, where we take a totient function that's the product of prime numbers. So let P and Q be prime. I want to find out what the totient function is for PQ. Can we derive it from the totient function for P and the totient function for Q? Well, if I multiply PQ, so PQ is going to be our n, if you like, the modulus. We're going to take the modulus with respect to PQ. Now the problem is that we've got multiples of P definitely in there, because we're going to have P times 1, P times 3, yep, but we've got 1, 2, 3, 4, 5, we got up to Q times P. All those we've got to eliminate. Similarly here we've got these will divide into PQ, Q times 1, 2, up to P. So we've got to subtract those. So we've got Q of those to subtract and P of those. But PQ is counted twice, so I've got to add one at the end. So what we've got is the Touchin function of PQ is PQ minus Q minus P plus 1. If you just rearrange these, you'll see that it comes to P minus 1 times Q minus 1. And guess what? That's just the totient function of the prime P. And we said P and Q are primes. So these are just the totient functions multiplied together. So we've shown that the totient function of PQ is just the totient function of P times the totient function, should be Q. Misprint there. I'll correct that later. Okay. What I want is, I want a message. I've got a message, say, here, and I want to raise it to a power E times a power D. But I'm going to do it in 2 stages, because I can choose E and D so that m raised to that power is m mod n. And we showed that if P and Q are primes, so E and D I can choose them as prime numbers, that this indeed is so here, that this will be m mod PQ. So I can take some message and raise it to some power here, P, and then raise it to another power. So what we could do, for example, is here take our message, raise it to the power E, take the modulus, and now this is C, our encrypted message. We take m as, say, 89, and now m times, and E is just some prime number that we raise it to that power, and now we've got an encrypted message. Now the wonderful thing is that we can choose a D that when we raise this encrypted message to that power mod n, we get the message back. So the trick is we need to be able to choose E and D, but we know that those can be just related to our totient function. Yeah, so we choose E prime and D prime. So E and D we can relate to this Touchin function for n. So n is going to be, in this case, E times D. Yep. Okay, so that's how it's applied with encryption. And we took a long time to get through there with our Modulus Arithmetic, but it's pretty amazing that the mathematicians back in 1650 and Euler a little bit later in the 17th century came up with these amazing mathematical theorems. Okay.